stress CT image-based computational model for quantification of myocardial blood flow in the human heart. We see your slides.
Okay. Thank you for the
well. Go on.
Okay. Thank you for the presentation. My talk will about the quantification of myocardial blood flow in human heart. Okay. Okay. Sorry. In clinical practice, the most used clinical parameter to evaluate myocardial ischemia is the fractional flow reserve, which determines the ratio between the maximal coronary blood flow through a stenotic artery to the coronary blood flow in a hypothetical healthy condition. However, it is an invasive technique since it requires the use of a pressure wire. Of a pressure wire to make the measurement. So recently, new techniques emerged to evaluate myocardial ischemia. For example, we have FFR CTE that estimates the FFR using computational fluid dynamics. However, it does not give any information about the perfusion inside the myocardium. Another technique is the stress myocardial CTP perfusion, and it calculates the myocardial blood flow, MBF, to identify ischemic region inside the myocardium. But it requires more CT scans and an intravenous stressor administration. So the aim of the work is to assess the reliability of a computational multiphysics perfusion model in reproducing MBF to have in future a non-invasive tool to quantify myocardial perfusion and to detect underperfused territories. So this here is presented the outflow of the presentation. We start with the geometry reconstruction that we proceed with mathematical and numerical modeling to parameter estimation, and at the end we present the results. About the geometry reconstruction, we start from CT images, and then we perform a semi-automatic segmentation to obtain the myocardium geometries. Whereas we exploit the vessel enhancement filtering from the work of Frangi to reconstruct the epicardial coronary arteries. In this way, we have the anatomical overall geometry. Then we define inside the myocardium the perfusion regions that are the territories of the myocardium that are fit by distinct epicardial coronary arteries. So we start from the terminal vessel of the epicardial coronary network, and we solve an economic problem to compute the distance of the terminal outlet from all the points inside the myocardium. And then we define the perfusion regions as the set of the points whose distance from the terminal outlet is the minimum among all the distance. Then, since from CTA we could reconstruct only vessel up to 1 millimeter of diameter, we needed to generate an intramural vascular network. So we use a volumetric filling network generation algorithm to generate the network, and to distribute the radius inside the network, we use the Murray law. Then we step to the mathematical and numerical model, and we adopt a multiphysics model in which for the blood dynamics in epicardial vessel, we use a 3D Navier-Stokes equations approach. Whereas for the intramural vessel, we model the blood dynamics inside such vessel using a multi-compartment Darcy model, in which that provides us an effective scale separation of the flow. In particular, we have a Darcy problem for each compartment, and each compartment is characterized by its own permeability tensor, and the compartments are coupled with a coefficient beta k that is the intercompartment conductance between the compartment I and the compartment K, and we choose to have 3 compartments. Then we need to couple the model for the epicardial vessel with the model of the intramural vessel. For this reason, we use 2 coupling conditions. The first coupling condition is related to the balance of interface forces, and the hypothesis is that the flow going out from the epicardial vessel to the intramural vessel is proportional through the pressure inside at the outlet of the coronary vessel and minus the first Darcy compartment pressure average. From this condition, we obtain a mixed pointwise defective Robin condition, and to complete the condition over gamma j, we impose null tangential tractions. The second coupling condition is related to the mass conservation. So we impose that the volumetric source of the first Darcy compartment is provided by the flow outgoing from the epicardial vessel. And here we have the overall coupled model, in which we have in red the Navier-Stokes equation. In green, we have the multi-compartment Darcy model. In blue, we have the interface coupling conditions. In yellow, we have the coupling conditions in the multi-compartment model. And in light blue, we have the sink term that accounts for the venous return at the end of the intramural vessel. Then we need to impose proper boundary condition. In particular, at the inlet of the coronaries, we impose a patient-specific coronary blood flow rate. The profile is shown here, and it is calibrated using patient-specific clinical data. In particular, the maximum coronary blood flow is set equal to the average myocardial blood flow in the myocardium for the volume of the myocardium. And then this profile is distributed between the left and the right epicardial coronary arteries, depending on the percentage of the myocardial volume perfused by the left and by the right epicardial coronary. Then we proceed to the discretization of the problem, and for time discretization, we use a BDF of order 1, whereas for the space discretization, we use finite element methods. And for the numerical solution, we propose an iterative strategy in which at each time step, we solve the two subproblems. In the first step, we solve the 3D blood dynamics inside the epicardial vessel, and we obtain the velocity and the pressure inside the epicardial vessel. Then we use this solution as input for the multi-compartment model, and we solve a curious media problem inside the myocardial domain. We obtain the solution of this model, and we iterate these two steps until a convergence criterion is reached. And next, we step to the parameter estimation. This phase is very crucial for the computational model, since we want to reproduce clinical data. We want to reproduce myocardial blood flow. So the parameter estimation that we propose is made by two steps. The first is an a priori parameter adjustment, in which we exploit the intramural vessel to estimate the permeability tensor of each compartment and the intercompartment coefficient inside the multi-compartment, and also the interface condition inside between the Navier-Stokes equation and the multi-compartment. In the second phase, that is the stress myocardial CTP guided parameter optimization, we use the MVF measured by images to optimize the parameter and improve the accuracy of the model. In the first parameter estimation phase, we subdivide the intramural vascular network in a distinct group of vessels, each one for each compartment. And we, for each node of the network, define a hierarchic parameter, and a generated node belongs to a compartment or to another, depending on the value of such hierarchic parameters. Then we start to compute the first estimation for the parameter. For the permeability, we use a porosity scale isotropic approach, in which means that the permeability is proportional to the porosity, and it is isotropic, and the porosity is estimated as the ratio between the volume of the vessel over the volume of the perfusion regions. Then we need to estimate beta k and alpha j, and to do that, we solve a Poisson problem inside the network. So for solve the Poisson problem, we estimate beta k as the ratio between the flow going out from the vessel of the compartment I to the vessel of the compartment K over the difference in the average pressure between the pressure in compartment I and pressure in compartment K. In similar way, we estimate the parameter alpha j as the ratio between the flow going inside the intramural vascular network over the difference between the pressure at the inlet of the intravascular network minus the average pressure in the first compartment. And both Ki and beta K are piecewise constant inside the myocardium, which means that they are constant inside each perfusion regions, but they assume different values inside the myocardium. The second phase is the stress myocardial CTP guided parameter optimization, and in this phase we use clinical data. In particular, we start from the myocardial flow computed, given us, provided us by the Centro Cardiologico Monzino, and we compute the average myocardial flow inside each perfusion regions, and we obtain what we define MDF-CTP. Then we step to the optimization procedure, in which we start from the value of beta E2 and beta 1,2 and beta 2,3 of the estimated in the previous iteration. Then we solve the perfusion model with a numerical simulation. We compute the myocardial flow as the flow that goes to the third compartment, that is the compartment in which nutrient and oxygen exchange happens, and we compute the relative error as the error between the computed myocardial flow and the measured by images myocardial flow. And then we optimize the parameter beta 2 and beta 2,3 in a way to reduce such relative error. For the results, we considered 9 subjects provided from Centro Cardiologico Monzino, and we had 4 healthy subjects and 5 stenotic patients. We performed the numerical simulation, and we analyzed the results from a modeling point of view, analyzing the absolute value of the relative error to evaluate the accuracy of our model. And then we propose, for a clinical point of view, a tetracalorimetry visualization of the results that allow us to detect and to evaluate ischemic region. In fact, in red, we have the regions in which the MBF is greater than 150 millimeter per minute for 100 millimeter of tissue. And the red zones are the healthy perfusion regions. Whereas in green, light blue, and blue, we present the ischemic regions with severity increasing from green to blue. So when we see these 3 colors, so we know that the perfusion regions is ischemic. Okay, in this slide, I reported 2 examples for the healthy subject, and we have in the first column the computed MBF. In the second, the MBF average from the CTP images. In the third and the fourth, we have the tetracalorimetry visualization for both MBF comp and MBF CTP. In the last column, we have the relative error for our simulation. And from a modeling point of view, we can see that the comparison between our models and the clinical data is very good. We found an excellent agreement between the solution, and also it is proved also by the relative error of our model that are below 6% and 2.2%. So the model has a great accuracy. From a clinical point of view, the tetracalorimetry visualization allow us to understand immediately that these are 2 healthy subjects. In fact, all the perfusion regions are physiological perfused. So the MBF is always over the threshold of 150 millimeter per minute for 100 millimeters.
Simone, keep an eye on time.
Okay. Yes. We now present the stenotic subject, and for a modeling point of view, we can see also that in pathological condition, the model can reproduce the clinical data, and from a clinical point of view, we can see that they are pathological subjects since they present hyperperfusion regions, and also the tetracalorimetry visualization allow us to understand that the patient P9 has stenosis that are more severe with respect to the patient P5. Here we present also the other 5 patients, and we can see that the accuracy of the model remains very high. And we can immediately see that P2 and P4 are ST subjects, whereas P6, P7, and P8 are stenotic subjects. These are the last results, and the error is always below the 8%, seeing this block plot, and the table on the right shows us that the average error is always below the 4%, and the low standard deviation prove that there is a low variability of the results. So the model can reproduce with a good accuracy the myocardial flow given by clinical images. So we are arrived to the conclusion, and we apply the multiphysics computational model to patient-specific scenario. We use real data for parameter estimation, and we found an excellent agreement between computational results and measured MBF. In future, we want to improve the parameter estimation to become independent on the stress myocardial CTP in a way to have a direct estimation of the parameters. And then, from a different point of view, we want to improve the model coupling with a myocardial contraction model. Okay, that's all. Thank you.
Thank you very much, Simone, for the very interesting contribution. Any question from the audience, or let me check, or in the chat to Simone? Yes, please.
So this was a great talk. I really appreciate you showing this. In regards to parameter estimation, yes. I feel because of maybe the coarseness of the perfusion map, you might run into identifiability issues where some of these parameters might not be uniquely identifiable. Have you looked into that issue with this data set in this model?
Okay, it's an interesting question, and I mean, we don't have such problem. I mean, the parameter that we estimated were unique. We can improve, or again, the accuracy of the model estimating this parameter, but in a few iterations of parameter estimation, we can recover the overall myocardial blood flow distribution. So,
okay, thank you.
Okay.
More questions to Simone? Let me check.
I have a question again.
Yes, please. Please.
I guess you also have the ECG of all these patients. Are these all these patients ST segment elevation patients, or do you also have these non-STEMI patients with it? And I would be very much interested in comparing which of these patients has a ST segment elevation. Did you check the ECG? I mean, this ECG.
Not really. We don't check the ECG.
Then I would suggest to discuss with the cardiologists and look at these pictures and look at the ECG and the ST segment, which is the easiest marker, of course, but has a slightly different value and scope, but it should go in some way hand in hand with what you're doing. But I would be interested how this fits together.
So just to check if we understand correctly your remark, which is very welcome. You are, let's say, considering or suggesting us that there is a correlation between the ECG and the perfusion maps. So yes. A non-well perfused patient should have, let's say, a perturbed ECG in some prescribed pattern that we could use also for, let's say,
yes,
tuning the model in some sense. Or
no, I think it's a different information that you get. Okay. I would say your work is great. Congratulations, I forgot that for the introduction. It gives an orthogonal view. And for the cardiologist, it would be very interesting to compare your results, your pictures, with the elevation of the ST segment, which is the standard measure for ischemic hearts. in fact.
We will certainly discuss that with the cardiologists. Thank you very much for your input. Really welcome.